Hi, everybody. This lesson is for Monday, March 30th. I hope you guys had a great weekend or are going to have a great weekend depending on when you watch this video. Um, just wanted to say hello. I hope you guys are doing well. Stay healthy. I'll switch over to our sort of intro sheet right now. All right, so intro and admin wise, so by today, by Monday, hopefully I'll be able to get you guys some feedback on homework 7 and in class 7. Not exactly sure what that's gonna look like yet, but I think my plan right now is to grade homework 7 for completeness. So if you turn it in, just note any specific issues, maybe sort of in your assignment, and I can try to take a closer look at that. In class 7, I'll try to grade more in detail and definitely get that back to you with plenty of time before I post the exam on Wednesday. Speaking of Wednesday, April 1st, this is not an April Fool's joke. Exam 2 will be available starting at 5 o'clock in the morning Eastern time. It'll be available for 24 hours. And again, take as much time as you need. I don't think that time should be a constraint on this exam. It's also open note, but I do please ask that you work individually. So don't, work with anyone else in the class or sort of, compare answers or anything like that. That being said, it is okay. I'll be on for office hours and it's okay to ask me questions about sort of the problem statement. Can I clarify what I mean? But that said, I can't tell you what a variable is for or anything like that. Last time on Friday, the lesson was about environmental loading. That'll be on the final, but no, it will not be on this upcoming exam. So today the plan is just to sort of review major concepts for exam 2, and we'll sort of, just talk about what to review, what to study, and then I'll kind of point you to some important handouts. So I'll go ahead and switch out of this and we'll get started with the notes. So this is sort of its own topic, so we'll just give it its own title, which is Exam to Review. And I'll slide up just a bit. Great. So the first question is, what's the format of this exam? I'm going to try to keep it as similar to our in-class exams with the caveat that since it's a take-home exam and you have a little more time to work on it, the problems might be a little bit longer or more detailed than the 50-minute exams that we have, for example, the practice exam, which was last year's exam. But again, expect something between, 4 to 6 FE style multiple choice problems, which are again, sort of, concepts, quick calculations, etc. Then also expect maybe between 2 to 4 free response, which will be longer, show your work, multi-part. Again, the exam will be open note. That said, I definitely recommend still making an equation sheet. I think that can be a really helpful way to organize, study, and then when you take the exam, it'll be a lot faster and streamlined. So I recommend making an equation sheet. And pooling together important handouts. So in particular, for exam 2, we've got a lot of equations that are sort of in tabular format or the API Cliff Notes. I would have those all in a common place, maybe API Cliff Notes, the individual stiffness matrix for bars in local and global coordinates handout, the fixed end force and moments handout. I would definitely recommend kind of, compiling those and having them in an easily accessible location. Again, the exam will be online and it will be available for 24 hours, starting at 5 o'clock Eastern Time on April 1, 2020. That being said, since it's available for 24 hours and it is OpenNote, I mentioned this earlier, but might be slightly more detailed than the practice exam. So then spring 2019 exam. Please be sure to try to submit via Blackboard, Google Classroom, or email by 5 o'clock Eastern Time on April 2nd, or give me lots of notice about why that would be impossible. Definitely I can work with you, but really important to bring any issues up with me well in advance. Let's go ahead and talk about major concepts or what to study. So major concepts or study tools. If you're going back and looking at lessons, this exam will cover lessons 13, 16 through 27, and 29. Lesson 28 was that environmental loading exam or lesson. And then also we'll have homework 5, 6, and 7, as well as in class 5, 6, and 7. Another thing to study also is going to be that exam to practice, which is posted under exam info on both Google Classroom and Blackboard. In Blackboard, you'll have to go to course materials, and then there's an exam info folder. Think all the way back before spring break, when we were still able to talk to each other face to face. That was when we started kind of the new material for this exam, which was the direct stiffness method. For beams and frames. I would say something that's pretty important with respect to this method is knowing sort of the progression of how we add these degrees of freedom. So again, from exam 1, we had axial loaded bars. We had trusses. That was a lot of S's. And now we have beams, frames. Again, all of this is in 2 dimensions. And if I think about how many degrees of freedom per node, for axially loaded bar, I'm only considering motion in one direction, so the X or the Y direction. So I only have 1 degree of freedom at each node. Trusses, since we're turning our bars at an angle, it's still axially loaded, but now we have 2 degrees of freedom. We could move in the U or the V direction. So we have 2 degrees of freedom. We have U and V. This would be the U prime direction, so in the direction of the bar. With beams and frames, we've added 1 more degree of freedom at each node. So we have U, V, as well as some rotation at that node theta. What that means then is my size of my system stiffness matrix. For axially loaded bars, it's always going to be N by N. For trusses, we have 2 degrees of freedom, so 2N by 2N. And for beams and frames, we'll have 3N by 3N. Similarly, our individual stiffness matrix. Sorry for the kind of wave there. Again, our individual stiffness matrix here, I have 1 degree of freedom at each node, 2 nodes per bar. So it'll be 2 by 2. Remember, this is our K, negative K, negative K, K. For a truss, we have 2 degrees of freedom at each node, 2 nodes per bar. 2 times 2 is 4 by 4. So for beams and frames, that individual stiffness matrix is going to be 6 by 6 for every single bar that I have. So how many individual stiffness matrices do we need? So how many individual, okay? And the answer for all of this is always going to be the same as the number of bars. So we'll call that B. And same for trusses, same for beams and frames. So again, kind of this is our framework for how we can organize these problems. I would say when you're studying the direct stiffness method as it applies to beams and frame, again, these are really long problems. I probably won't say, you know, here's a frame, go ahead and solve for everything. But I will probably maybe ask you to solve parts of the problem. So know parts of the problem and the general framework of the solution. So first we define our nodes and bars, then we set up our individual stiffness matrices, then we form our system stiffness matrix, then we can apply boundary conditions. For this problem, for beams and frames, we also have to consider fixed end forces and moments before we write our system equation. And then we can start partitioning and solving. So just have a look at kind of the examples and the homework about how we step through each portion of the problem. Also sort of know how to talk me through. So if I give you a really complicated frame, talk me through how many individual stiffness matrices do I need? How big will my system stiffness matrix be? How big will my system equation be? What will that look like? Another important concept for this is how to find my angle of my beam. So my angle, now we call this phi or phi, in global coordinates for an inclined beam on a frame. Also know whether you need to use local or global coordinates. So find parts of an individual stiffness matrix in local or global coordinates. And I think there's a practice problem on the practice exam that asks you to find 2 elements of an individual stiffness matrix in global coordinates. Other important things, applying boundary conditions based on external loads and supports. And then finally, especially new for beams and frames is finding the equivalent fixed end forces and moments due to mid-span loading and applying in system equation. So remember, for beams and frames, our system equation changes slightly, where now we have our vector of forces is equal to our system stiffness matrix. So again, this is going to be 3n by 3n times our vector of displacements plus our vector of fixed end forces and moments. And we can use the table from the handout. I'll show that at the end of this lesson to find that vector of fixed end forces and moments depending on any load condition. Remember that you can use superposition to find fixed end forces and moments for complicated situations. So for example, if I have something that looks like this with a distributed load and a point load, and this is L over 2. This is equal to the fixed end forces from my uniformly distributed load across the entire beam, plus the fixed end forces and moments due to this point load applied at L over 2 across my beam. So we had some examples on that in homework 5. Please don't hesitate to let me know if you have questions during office hours anytime today, and definitely happy to meet as needed, on Tuesday as well. Let's shift this up. I keep kind of some of the previous notes. Great. All right, so after we finished the direct stiffness method for beams and frames, we moved on to our unit on STAAD. Again, this was still before spring break, so we all had STAAD access to our computers. I mentioned this, I sent an email out that we do have VPN access, so we should be able to use STAAD moving forward for our projects. That being said, I want to take some time to test that the virtual network works, that it's stable, and so probably expect a slightly smaller emphasis on STAAD than having to solve problems in STAAD or anything like that. That being said, I think anything that's in the tutorial, homework assignments, so that would be homework 6, in class 6 especially, and the exam 2 practice is a great way to study. Any of those sort of like fill in dialog boxes, interpret results, or command file. I think all of those types of questions are fair game. Also know the overall framework for setting these problems up in STAAD. So again, first we have to define our nodes, and then between our nodes, we can define bars, we define material properties using a user table, how we define supports, how we define loads, make sure you're careful with your dimensions and units, things like that. So again, defining nodes, bars, cross-sectional properties, supports. Remember, we used a fixed butt support to represent a roller. Fixed and pin are self-explanatory. Also, distributed loads. So we have nodal and member loads. STAAD calls these joint loads. And then again, interpreting the results. So definitely have a look at this previous material. Let me know if you have questions on what I expect you guys to know for STAAD. And then finally, most recently, we've had some lessons on API, the American Petroleum Institute design of columns. Here, I would say, have a look at homework 7 in class 7. It's important to know all of the checks, but also be comfortable jumping in to solve a part of the problem. So if I have already done the axial check and I told you, here's your allowable compressive stress, here's your actual compressive stress, can you do a combined check giving information for the bending stress and knowing what you know about when you have to apply checks for the P delta effect. So solving parts of the problem. Also, like in class 7, when you had to find the maximum moment, finding threshold values. given info on allowable or actual stresses. So for example, if I were to give you something like the allowable, you know, the critical hoop buckling stress, could you find the maximum depth, or could you find the, you know, minimum thickness of the structure? So example, max depth to satisfy hoop stress, check. Maybe the minimum length for an Euler column, given your critical slenderness ratio and some other information about the column, like the diameter and the thickness. Max moment for bending check, that was what in class 7 was about, etc. Honestly, those are the 3 big picture concepts. So expect, you know, sort of equally distributed between everything. Again, maybe STAD a little bit less, maybe more dialogue boxes, kind of supplementing the stepping through the direct stiffness method by hand. I'm going to go ahead and switch over to the computer. So I'll go ahead and share my screen because I did want you guys to see just if I go to Blackboard. So let me go here. Here we are in Blackboard. So if I go back to the announcements, I think this is sort of what you guys see in Blackboard. And if you go to course materials, you can go ahead and have a look. So this is all the lesson material, lecture notes. If you look at in-class PowerPoints and handouts, I might go ahead and pull out some of the important handouts. So one of those handouts that's really important is this beam and frame local and global stiffness matrices. So this is our combined stiffness matrix for local coordinates for a beam or frame. Again, this is an individual stiffness matrix, 6 by 6. This shows that we can combine our axial loading and our bending global coordinates to form this really big global stiffness matrix that combines axial and bending. So this is our most general matrix for any beam and frame load, displacement, translation situation. So this is definitely a handout you'll want to have handy. Another important handout is this fixed end forces and moments table. So again, you know, expect me to present some of these cases or maybe some superposition of these cases and solve for fixed end forces and moments, or given the moments, can you solve for this load or can you solve for the length? So be able to kind of rearrange these equations. And then finally, if I go back to in-class PowerPoints and handouts, I think the very last handout that will be very useful, well, I guess 2 more. So the STAD tutorial, you know, just being able to step through this process and knowing these dialogue boxes is important. And then finally, the most recent handout that's important is those API design cliff notes. Feel free to pull, you know, the full design guidance, but the important stuff for this class is these cliff notes, which kind of step through the axial compression check, bending check, hoop stress check, shear check, I think we already scrolled past, and combined stress check. So that's really it for exam 2. If you guys have any questions, please don't hesitate to reach out to me today in office hours, tomorrow. I'm happy to meet up for office hours. And Wednesday, I can really only answer questions about, you know, what are you asking me to solve for in this problem? But I'll be on for office hours that whole time, so feel free to jump on and, you know, clarify anything with me. I hope you guys have a great day. Good luck on the exam. And please don't hesitate to let me know if you need anything. So thanks so much again, and looking forward to seeing you all soon.